Hey everybody, this week we're going to be talking about parsing, the PCFGs, and machine translation. So without further ado, let's jump right into it. So in the last couple of weeks, we've dived into a couple different areas. And this week we want to focus primarily on some of the more fundamental parts of NLP. We want to focus on the parsing part. We want to focus on the probabilistic context-free grammar, or the PCFGs, and the machine translation. These are key components of in understanding how the NLP systems actually process language to understand structure, resolve ambiguity, and perform more complex tasks such as translating text between different languages. Let's take a moment to review the learning objectives for this week. And by the end of today's session, you'll have a solid understanding of these four concepts. You'll be able to explain what parsing is and why it is important in NLP. Parsing helps systems break down sentences into structural compounds, which allows the machine to understand and generate language more naturally. Next, we'll explore how the probabilistic context-free grammar, or the PCFGs, are used to resolve the ambiguity in different ways and the challenges that arises when sentences can be interpreted in multiple different ways. Finally, we'll then connect all of this using machine translation and other advanced NLP applications where parsing plays a vital role in understanding and producing accurate translation. Next, let's jump into what is parsing. So parsing is one of the most foundational processes within the NLP. In simple terms, parsing refers to process of breaking down a sentence according to the rules of a grammar. This helps a system understand the structure of a sentence, essentially how all of the individual words fit together to create the meaning. Just as we as humans subconsciously apply grammatical rules to interpret language, NLP systems use parsing to break down a sentence into its base form. There are two primary methods of parsing in NLP: constituency parsing and dependency parsing. Constituency parsing breaks a sentence down into a larger unit called the constituents. There are typically phrases like nouns, like noun phrases and NP, as we had before, or verb phrases, VP. This type of parsing helps us understand the hierarchy structure of a sentence. Dependency parsing, on the other hand, doesn't focus on the phrases, but rather of the grammatical relationship between two individual words. It identifies how words in a sentence are linked, such as how a subject relates to its verb and how an object are connected to an action. Each approach has its strength and is suitable for different tasks within NLP, which we'll explore in more depth as we move forward. To put it in perspective, think of constituency parsing as creating a map of phrases within a word, breaking it into chunks like noun phrases and verb phrases. And dependency parsing, on the other hand, is like mapping out the grammatical relationship between each word. So for instance here, in a sentence like the cat chased the mouse, dependencies parsing would show that the word chase is the main verb, with cat as a subject and mouse as the object. So let me say that one more time. So in this dependency parsing will show that chase is the main verb, and that the word cat as the subject and the word mouse as the object. These relationships are crucial for understanding not just the meaning of individual words, but how they function together to convey the complete thought. Next, let's actually look a little bit deeper between the two relationships here and how both types of these trees often offer different ways of representing the structure of a sentence, and each how they specify their uses within NLP. A constituency tree represents how a sentence can be broken down into phrases. For example, the cat chased the mouse. The tree would first divide the sentence into a noun phrase, NP, the cat, and the verb phrase, VP, chase the mouse. Then each of these phrases would be further broken down, with the noun phrases being split into denominators. The word the and a noun, cat, and the verb phrase splits into verbs, chased, and the object of the verb, the mouse. This hierarchy shows how sentences are composed of nested structures, which particularly useful when systems need to understand complex grammar construction, such as embedded clauses. On the other hand, a dependency tree focuses on the relationship between individual words. Instead of grouping words into phrases, it maps out which words are dependent on each other. In the sentence, the cat chased the mouse, the dependency tree would show that the word chase is the main verb, and that the word cat is the subject of that verb, while the word mouse is the object. This approach is more considered with the grammatical function of the word. Who is doing what to whom, when we think of it like that. And in dependency phrase within dependency parsings is especially useful in tasks like information extraction or machine translation, where understanding word-to-word relationship is crucial for generating accurate outputs. If you think about it again, another great way to think of this is when you are submitting your resume online, and sometimes that it'll ask you to upload your resume, and then it will automatically fill in some of the blanks if you go on with the application. That's parsing in this beautiful form right there. That's one of the benefits of it. Next, let's talk about a real-world example. So in this example, we'll kind of look at how virtual assistants like Siri and Google Assistants parse a sentence to understand and respond to a request. So let's take the input, can you schedule a meeting for me tomorrow? For a system to process this query, it first needs to break down the sentence, down into a structural component using both the contingency parsing and dependency parsing. Within the first one, the contingency parsing, the assistant starts by identifying the phrases in the sentence. In this case, the phrase "can you" would be tagged as the mode phrase, MP, signaling a question, while the phrase "schedule a meeting" forms a verb phrase, VP. For tomorrow, that phrase would be a prepositional phrase, PP, modifying the verb, indicating the time of the meeting. Consistency phrasing gives us a top-down view of the sentence, identifying these large chunks to determine the sentence's grammatical structure. And then we think about how would it really work within the dependency parsing. After identifying the phrases, the system would need to map out the grammatical relationship between the words. This involves determining who is performing the action, what is the action, and any objects or modifiers related to that action. In this case, the word schedule is the main verb, while the word you as the subject, the person scheduling the meeting, and the meaning as the object, the thing that's being scheduled. And the phrase "for tomorrow" as the time frame modifying the schedule. This word-to-word relationship gives the assistant detailed information about the user's intent. By combining these two types of parsing, the system is fully understanding what the user's query is and can provide a more coherent response like, "I scheduled your meeting for tomorrow." Parsing ensures that the systems not only understand the individual words, but also how they interact in a grammatical context, allowing the natural and effective communication. Next, let's jump into probabilistic content-free grammar, or the PCFGs. A context-free grammar, or the CFG, is one of the simplest and the most widely used tool within NLP systems to understand the syntactic structure of a sentence. It operates using a set of rules that break sentences down into smaller, well-defined compounds. These rules provide a clear and construct way to represent how words in a sentence relate to each other, according to a specific grammar. Take, for instance, the rule S within then NP. Oh, sorry. So let's think about this one more time. So, for instance, take the rule S going to NP, VP. This means that the sentence S is made up of a noun phrase, NP, followed by the verb phrase, VP. The noun phrase would be something like "the cat The verb phrase will be something like chase the mouse. The CFGs are designed to capture these basic relationships between parts of speech to help understand how sentences are structured. So take a look at the example and kind of think about what I just said. So when we have a noun phrase, that could be something like the cat, and the verb phrase could be something like chase the mouse. So as a quiz question, I could provide a sentence and I could ask what is the verb phrase and what is the noun. So think about that as you kind of go along. To visualize this, we use what is called a derivation tree or parse tree, as we talked about before, right before this. This tree starts with the sentence at the root, and as the grammar rules are applied, the tree branches out into phrases like NP and VP, and then into individual words like cat and chase. This hierarchy structure shows how each word fits into overall grammar of a sentence. However, while the CFG gives us a structured way to parse sentences, they lack the ability to deal with ambiguity, which is where the probabilities come in. Okay, so while the CFGs provide a structured way to parse sentences, they can't really handle one of the most common challenges in languages, and that is ambiguity. For example, let's consider the sentence, I saw the man with the telescope. This sentence is ambiguous because it means either that I used a telescope to see the man or that the man had a telescope. This is a kind of ambiguity that is a common occurrences in natural languages. And resolving it requires more than just a simple set of grammatical rules. And this is where probabilistic context-free grammar, or the PCFG, comes into place. A PCFG is an extension of the CFG that assigns a probability to each grammar rule based on how often that the rule appears within the corpus of the text. So for an example, the system might learn from a large data set that it's more likely for the word or the phrase with the telescope to describe that the man rather than the action of seeing. By applying probabilities, the systems can select the most likely interpretation of a sentence. In the case of I saw the man with the telescope, the system uses the probabilities associated with each potential parse to determine whether it's more common to interpret with the telescope as modifying saw or man. By leveraging probabilities, the PCFGs help systems resolve ambiguity and choose the most plausible structure for a sentence. Okay, so now let's talk about ambiguity in the real world of parsing. So in the situations as we talked about before, such as I saw the man with the telescope, the PCFGs are incredibly helpful because they allow the systems to assign probabilities to different interpretations. The system doesn't just guess at random. Instead, it uses information from a large data set of previous encountered sentences to determine which interpretation is more likely. So for instance, if the database saw that with the telescope is more commonly used to modify the word man, then the system will lean towards that interpretation. So real world applications of this is like Google Translate or the speech to text systems that often face this kind of ambiguity. And the PCFGs are a powerful tool to resolve some of these issues. So if you ever had it where you can just simply now talk to your phone and it will write out the messages, but you've noticed that sometimes it just doesn't get it right. So you have to consistently teach the model how to properly say something. It could be somebody's name. It could be a certain slang that you typically use. But these text-to-speech systems often need more information. And same thing goes with other systems like a Google Translate. So by selecting the most probable phrases, the PCFGs ensure that the system generate the most contextual approach on an output. This probabilistic approach is a key to improving the accuracy and influences how machine generates language. All right, next, let's talk about a little bit more advanced parsing techniques. Let's now look at chart parsing and the CKY algorithm, which are two techniques that use to handle more complex parsing tasks effectively. As sentences grow longer and more complex, it becomes computationally expensive to parse them from scratch repeatedly. This is where chart parsing comes in. It uses dynamic programming to store and reuse intermittent parsing results, saving both time and computational resources. One of the most popular algorithms in chart parsing is the CKY algorithm. The CKY algorithm takes a bottom-up approach, meaning it starts by identifying the smallest compound of a sentence, like individual words or small phrases, and generally build up to the larger parse tree. Each possible parse is stored in a parse chart, which allows the system to reuse these intermediate results without recalculating them. For example, if the system has already parsed a noun phrase, like the word the cat, it doesn't need to reparse it, that phrase, when it's part of a larger sentence. Instead, it can pull from its stored results and move more effectively. The CKY algorithm is essentially useful in systems that uses the PCFGs because it can effectively calculate all possible parses and their associated probabilities. This makes it a key tool for a large system, a large-scale NLP application, including a machine translation, speech recognition, and an information extraction, where sentences can be longer and more complicated. So what are some examples of this? So let's walk through a concrete example of the CKY algorithm in action. We'll parse the sentence, the cat chased the mouse, step by step. First, you'll need to initialize. The CKY algorithm first creates a parse chart, a grid where each cell represents a possible substructure of a sentence. The row represents starting position in a sentence, and the column represents the length of the phrase being parsed. The algorithm starts by placing the individual words into a dialog cell of the chart. So for instance, the word the would be labeled as a determiner, DT, the word cat as a noun, and so on and so forth. Then we're combining the substructures. From there, the CKY algorithm begins combining these individual words into larger structures based on the grammatical rules. So for example, the phrase the cat becomes a noun phrase, NP, and the phrase chase the mouse becomes a verb phrase, VP. These combinations are structured in a chart, so you don't need to recalculate this if you're using it again later on. And then the final parsing tree. So the algorithm continues to combine the substructures until it has built the complete parse tree for the sentence. In the final tree, the phrase the cat is identified as a subject NP, and the word chased is the verb VP, and the phrase the mouse as the object which is known as the NP. The CKY algorithms ensure that the systems can effectively parse the sentence by storing and reusing subparse, making it ideal for handling sentences that might have multiple valid parsings. So this dynamic programming approach is essentially for large-scale NLP tasks where parsing needs to be done more effectively and more accurately. We'll spend some time in the following weeks to actually really go and dive deep into the CKY algorithms, and I'll show you a diagram of how they actually work in real time. Next, let's finish up the section by going into machine translation. So as we shift our focus to machine translation, MT, one of the most widely used application of NLP, machine translation is the process of automatically converting text from one language into another, as seen in tools such as Google Translate and DeepL. While the idea of translating between languages might sound simple, it involves several complex challenges. Different languages have different word orders, grammatical structures, and expressions, all of which makes translating super difficult and such a complex task for systems. For example, in English, the typical use of a subject verb object, or the SVO word order, as the cat as in the phrase, the cat chased the mouse. In Japanese, however, the structure is a subject-object-verb, which is the SOV, meaning that the sentence would translate to the cat, the mouse chased. Parsing plays a crucial role in helping the machine identify these sentence structures, so it can reorganize and then it could generate a grammatically correct sentence in the targeted language. So if you go into Google Translate and you try to, type a word, so let's use the phrase here, the cat chased the mouse. If you put that in English and you want to guess to translate into Japanese, in this example, it would probably translate back into the cat the mouse chased. So how do systems understand what's going on? So if you ever use this Google Translate and you wanted to translate something, you always got to double check that the grammar is correct. But the challenge doesn't stop at the word order. Ambiguity and kind of different expressions further the complications of translating processes. Ambiguity within a sentence, like the chicken is ready to eat, requires the system to determine whether a chicken refers to food or the animal itself. Phrases like kick the bucket can't be translated literally because their meaning is figurative. Systems need to recognize that these phrases and it needs to find the appropriate expression within the targeted language. We'll dive deep into it and kind of talk about different challenges that arise. So when we talked about a couple things already and how these different parsing systems kind of play into machine translation. So within the first method, right, we understand that it helps break down the words into larger phrases, as we talked about before, right? And such as the noun phrase NP and the verb phrases VP, and understand the overall structure of the sentences. So for instance, again, in the English, we follow the SVO pattern. It's different in Japanese, where it follows more of the SOV order. So the system can reorganize and rearrange the compounds, preserving the meaning of the word. The system focusing on larger structure. In this first parsing, we understand that it ensures that the phrases remain intact and grammatically sound in its targeted language. And then we talk about the dependency parsing as we did before. We focus on the word-to-word relationship here, and it ensures that the key grammatical roles, such as the verb, subject, and objects, are maintained across different languages. So again, for an example, in the sentence, the cat chased the mouse, the dependency parsing identifies chase as the verb, the cat as the subject, and the mouse as the object. While translating into another language, these roles must stay consistent, even if the word order changes. Dependency parsing guarantees that the relationship between the words are preserved so that the translation reflects the intended meaning. So, and I also want to add here that the PCFGs also helps with ambiguity, right? And it plays a major role in how sentences are often have multiple interpretation. So the PCFG helps the system choose the most probable based on the statistical patterns. So there's a lot happening in the back end. Again, for an example, if a phrase like with the telescope could either modify a verb or a noun, PCFGs use the probabilistic data to determine which interpretation is more likely, even if we translate it into a different language. The sentence needs to be more contextually appropriate. Cool. So how does this work in the real world, right? So let's take a real world example of machine translation. And the action of the word, I saw the man with the telescope, as we discussed before, this sentence is ambiguous. And it means either that I could use a telescope to see the man or that the man had the telescope. While translating this sentence into French, the system needs to resolve this ambiguity and chooses the correct structure for this translation. So what needs to happen first, right? So first, the system applies the contingency parsing to break the sentence into key components, such as the word I as the subject, the word saw as the verb, and the phrase the man as the object. And with the telescope, the phrase with the telescope as the prepositional phrase. Once the system has identified these components, it uses the dependency parsing to map the relationships between the words that needs to, and with this, it helps determine whether the telescope describes the man or the action of seeing. So then we actually get into how handling ambiguity with the PCFGs. So the system then uses the PCFGs to analyze the probability meaning of the sentence. Based on the trained data model, the PCFGs might determine that it is more likely for the phrase with the telescope to modify the phrase the man, meaning that the man had the telescope. This system assigns a higher probability to the interpretation and selects its appropriate structure. And then finally, the output needs to come out is that even with the ambiguity resolved, the system generates a final translation. And this sentence, and when it gets translated into French, this sentence will then be able to accurately reflect the meaning that the man had the telescope. By using parsing and then by using the PCFGs, the system ensures that the translation maintains the original meaning, even when the sentence structure or ambiguity might differ between languages. And with everything that we talked about, right? There's a lot of challenges here, right? There's ambiguity, there are expressions, there are the word orders. Different languages have different grammatical structures. Again, English with the SVO and Japanese with the SOV. So it's super important to just understand that there are going to be a lot of challenges, and then using different data sets and making sure that your systems fully understand what's happening using different just a large amount of data. This will kind of help reduce some of the challenges within machine translation. I think we take some of the things that we have now for granted as things that are just common. Again, with Google Translate, we automatically just assume that it will translate things for us appropriately, but that's not always the case. And with everything that we've talked about so far, when it comes to parsing and when it comes to the PCFG, we want to make sure that from the top to the bottom, that the machine systems can understand what we're talking about. So parsing to then probability to then translation, all of these kind of play into what we want to do and how the systems talk to each other. Great. So we're at the end of the lecture for this week. So the following weeks, we're going to get a little bit more into more complex topics, and we're going to get into more of algorithms and kind of more understanding how different applications can be used within the world of NLP. And we'll even talk about some cooler concepts as the weeks go on. So if you have any questions, please feel free to reach out. Thank you.